The sea has always enforced an unbreakable law of physics on every conventional warship. Despite millions of horsepower pouring through their screws, a massive destroyer, with its broad, displacing hull, struggles fiercely to push past the 35-knot barrier. Beyond this speed, the amount of engine power required to overcome water friction and wave-making drag, where the ship is effectively climbing its own self-generated wave, rises exponentially. This limitation created a dangerous strategic impasse for the U.S. Navy, particularly in the vast theaters of the Cold War, where faster engagement and quick retreat were paramount. Conventional ships were simply too slow to intercept the new generation of lightning-fast Soviet attack craft and were vulnerable on long-haul patrols. The very nature of a displacing hull meant a fundamental compromise: speed or armor, but never both. Watching this struggle unfold from the perspective of an unconventional engineering mind, the mechanic solution seemed obvious, yet completely impossible to the naval establishment. He realized that if you couldn't beat the friction, you had to remove the hull from the water entirely. This was the core of the outlawed idea, the hydrofoil. He envisioned a vessel lifted completely clear of the surface, supported only by submerged, wing-like structures, the foils which generate lift in the water the same way an airplane wing generates lift in the air. This would drastically reduce drag, allowing a ship to achieve speeds previously relegated to aviation. Predictably, the concept was met with utter ridicule from the brass. Senior Navy admirals and established naval architects saw the design as an unnecessary, complex, and fragile deviation from centuries of shipbuilding tradition. They dismissed the hydrofoil as a gimmick, too unstable for high seas, too vulnerable to debris, and too dependent on unproven systems. The mechanics' drawings were shelved, the math questioned, and the idea of a combat ship flying above the water was deemed structurally unsound, impossibly expensive to maintain, and completely unfit for the rigors of naval warfare. The challenge was now not just one of engineering, but one of convincing a deeply conservative institution that the fastest way to travel across the sea was no longer in the water, but above it. The transition from blueprints to operational reality was marked by spectacular failure. The early, unstable prototypes were nightmares of engineering complexity, often consisting of repurposed boats fitted with crude, fixed hydrofoils. Testing was terrifying, not elegant. These initial vessels, attempting to achieve flight speed, would leap violently out of the water, crash back down with bone-jarring force, or veer dangerously off course, proving to the skeptics that the idea was indeed too unstable. The engineers quickly learned that merely generating lift wasn't enough. They had to master the physics of flight on water. They recognized that a hydrofoil wing generates immense lift, but it requires continuous, instantaneous adjustment, a degree of control impossible for a human pilot to manage manually. As speeds increased, a new catastrophic problem emerged: the cavitation crisis. Standard propellers, designed to push ships through water, simply vaporized at the high, rotational speeds required for foil-borne operation. Water pressure would drop, forming superheated bubbles that immediately collapsed, chewing away at the metal and destroying the propellers within minutes. This destructive phenomenon led to immediate funding, failures, and fury. Documents reveal canceled test runs, massive budget overruns, and powerful condemnation from traditional shipbuilders who saw the hydrofoil program as a money pit. The engineer faced not just the laws of physics, but the powerful institutional resistance that thrives on failure and complexity. Despite the near-constant threat of cancellation, the team persisted. They introduced advanced, supercavitating propellers designed to deliberately ride on top of the vapor bubbles, and began integrating complex, automated control systems. Finally, after years of setbacks, they reached the tipping point. A later prototype, equipped with sophisticated avionics, gyroscopes, and computers adapted from aerospace, managed to stabilize the hull. With the foils fully submerged, the vessel rose smoothly onto its stilts, lifted completely out of the choppy surface water, and accelerated gracefully. It maintained a stable, high-speed run, proving once and for all that a ship could not only fly above the waves, but do so with controlled, sustained speed, the first true victory over naval friction. The technological success of the prototypes suddenly collided with a looming strategic crisis, the threat from the East. During the Cold War, the U.S. Navy was seriously concerned about the speed and stealth of new Soviet fast-attack craft, small missile-armed patrol boats designed to overwhelm slower, larger targets. These Soviet vessels posed a threat that conventional American destroyers, constrained by the 35-knot barrier, could not counter effectively. The need for a rapid, surprise attack deterrent, capable of high-speed interception and immediate repositioning, became paramount. The hydrofoil, once ridiculed as a gimmick, was now seen as the only viable solution to fight speed with overwhelming speed. This strategic pivot led to the birth of the Pegasus, the official designation for America's first patrol hydrofoil missile (PHM) ship, the USS Pegasus PHM-1. This was no longer a crude test platform. It was a compact, lethal warship designed entirely around the OUTLAWED. Its combat role was unique: to carry massive offensive firepower, like Harpoon anti-ship missiles, and deliver it faster than any other vessel, striking before the enemy could react. To achieve this unprecedented speed, the Pegasus relied on a complex and powerful propulsion system, presenting a major engineering hurdle in the power plant challenge. Unlike conventional ships powered by steam turbines, the Pegasus used a specialized gas turbine engine, essentially a modified jet engine, to provide the 17,000-plus horsepower needed to lift the hull onto its foils and sustain foil-borne flight. This massive power plant was tightly packed into the small hull, a feat of miniaturization required to maintain the ship's light weight. Furthermore, maintaining stability at over 40 knots required far more than just powerful engines. It required the automated brain. Engineers incorporated a highly complex hydrofoil control system using gyroscopes, sensors, and computers adapted from aircraft avionics to continuously adjust the angle of the submerged foils multiple times per second. This stabilization system was the secret that turned an inherently unstable design into a smooth, high-speed missile platform, granting the Pegasus the ability to fly safely in high seas. The moment the USS Pegasus began its speed trials was the culmination of decades of unconventional design and institutional struggle. The sight of the ship lifting off the water was breathtaking. As speed increased, the massive hydraulic actuators retracted the main foils, causing the hull to cleanly rise and transition from displacing the water to flying on its underwater wings. It was a fusion of marine and aerospace engineering. Once fully foil-borne, the ship unleashed its full potential, creating a visible speed shock in naval circles. Reaching speeds of over 40 knots, a massive leap over the 30 to 35-knot limit of conventional destroyers, the Pegasus earned the immediate, undisputed title of America's fastest operational warship. This speed translated directly into a new tactical paradigm. The Pegasus operated as the Tactical Ghost, a lightning-fast platform designed to use its speed to approach heavily defended coastlines, fire its Harpoon missiles, and vanish before the enemy could register a counterattack. Its speed allowed it to outrun any torpedo or conventional patrol vessel, embodying the philosophy of hit-and-run warfare. Even in high seas, the complex control systems maintained a level of stability superior to hull-borne vessels of comparable size, allowing it to maintain operational readiness when other ships were forced to slow down. This incredible performance cemented the Outlaw's legacy, demonstrating the victory of radical engineering. Although the hydrofoil program was eventually retired due to high maintenance costs and strategic shifts, the technology fundamentally changed naval architecture. The final conclusion remains: the single mechanic's outlawed idea successfully conquered the friction that had bound naval power for centuries. The hydrofoil proved that with enough determination and unconventional thinking, the very laws of physics that govern the sea could be defeated, creating a class of vessel that still stands as a testament to the fact that radical solutions often require ignoring the established wisdom of the past. The Pegasus may be retired, but its performance remains an unmatched benchmark in naval speed.